So session like hello, am I audible? Okay. So in the previous session, we were looking at various regularization methods. So one of the main objective of regularization is to reduce the variance. So bring the variance down, and that is why we do this regularization. One technique to do this is to perform telescoping. So one way to do this is by early stopping. So in this technique, like what happens is both the training set and the set cost, both of them are plotted together for every iteration. So after some time, the dev set cost will stop decreasing. So basically, like we will have a thing like this. So after some time, the dev set error will stop. On the other hand, training set would have decreased with respect to the number of. So now the place where it stopped decreasing, so that weight is considered, right? So we will pick the point at which the training set error and dev set error are best. We will take these parameters as the best. So this is one another way. So So you try to basically, like here, we see that this is overlearning that is happening. Okay? So this is overlearning that is happening. So it means these weights are so optimized for the inputs. So we stop here itself. So don't allow the weights to be so optimized. Rather, you stop at this particular point and take the weights at this point, and you try to say this as the final weights. So now the problem is that here what happens is this particular technique does two things. One is we are trying to both minimize the cost. So this is the minimal point, right? So this is minimization of the cost, as well as we are trying to reduce the overfitting. So it means that both of these are simultaneously tried to be done. So you try to minimize the cost as well as you try to overfit. So now this is not very ideal approach. So that is the problem with respect to this release topic. So either you minimize the cost or you try to reduce the overfitting, but don't do both of them, right? So that way, like this is not very preferred approach. So similarly, like you can also go for a model. So one another way in which like you try to speed up the training process is to go for normalizing. You can also normalize the say for instance I can have the inputs the features may be of different range, maybe one is ranging from 1 to 1000, one is ranging from -1 to 1, right? So one may be 0 to 10. So you may have different inputs. So that if all of them are say 0 to 1, -1 to 1, true, false, and so on, like maybe this may be acceptable. But then when the range is very high, then there will be a need for normalizing the. So um, so that way it will speed up the training process. Uh, normalization, what we do, like we try to compute the mean, right? So for a particular feature, like compute the mean of the feature and then subtract the mean from the. So this is one particular step, right? So the next step what you do is try to compute the variance. So basically, like if you have the input that is in this case, so when you do the in subtraction, then like maybe you try to get them at this. Then you also remove the variance. So then eventually like you have the points at this position. So it means that you try to normalize with the mean as well as you try to normalize the variance. Right? So one thing like somebody was asking if you have a hands-on. So I'll try to cover this up as much as possible, and I'll see like what I can do. So now, why do we normalize? Right. So now, before we look at why we normalize. So we see that like these should be applied for all the three things, right? So training, dev, and test data sets. So by using mean and variance of the training set, if you are performing normalization, then you need to perform on all the three different sets. So why normalize? So if we do not normalize now, the cost function will be and the shape will be consistent. Say for instance, like if you have the cost function, if one of the variables is very large, then you may have a cost function which will be like this. Right? So maybe like it will be a squiggly kind of a shape, and you may have the contour of this cost function, like which may be circles. So maybe like you have the cost function which is in this kind of a form. So so now the counter will be in this kind of a form. So on the other hand, when you do a normalization, you may have the cost function which will be of this form, and you may have your cost function contour which may be very symmetric. So it may be symmetric. So what is the advantage when you do this normalization? So when you normalize the movement from any point to the minima is going to be smooth. Right. So here you have a consistent cost function. So now, and so in that case, we can use larger learning rate and the optimization. So in here, like if you use a larger learning rate, then it may overshoot, right? So now over here, like you use a larger learning rate, it may straight go towards the so that is one of the advantages in using this kind of normalization. So another thing is the vanishing and the exploding gradients. So right now we are looking at some of the ways in which like we can increase the convergence, and here like we look at this problem which is called as the vanishing or exploding gradients. So here what happens is that say you may have work. So so let's assume that we have a tube neural network, and the number of layers of this network is here, and all the activation functions are linear, and each is equal to 0. So in this case, like say for instance, you have um, so you have a deep neural network. And now let us see that all these all these layers and all the activations are so if all the activations are linear, then what are we going to have? So this is going to be Z1, right? So we're going to have Z1. And then going to have A1 is going to be equal to G of Z1, and this is going to be equal to Z1 because we saw that the activations are linear, right? So now we may then this. So this is going to be W into A1 because the output of this is going to. So this is going to be equal to Z2. Then this is going to be equal to A and so on. Right? So we're going to have a network like this. So now, if you look at, so it's going to be some kind of composition of all these weights, which is going to be. So now, now we're going to have W. So now, if the weight in each one of the layer is, say, for instance, 1.5, 1.5, 0, 0. So if you have this weight, maybe like for all these weights, you will have this kind of form X for this weight, right? So this weight is going to be of, say, a vector weights. Rest of all are four weights. So rest of all you have four weights, and here you have two weights. So let's assume like you have this weight, and because of this composition of weights, you're going to have a weight which is going to be 1.5, 0, 0, 1.5, and this is going to be L minus 1 into S. So let's assume this weight, this last weight as WL. So we are going to have WL into this whole weight into X. So now what is going to happen is that we are going to compute 1.5. So now what this is going to give is a very large value for y cap. So you compute all of this to finally find out y cap. So now this is going to give, since by virtue of this being greater than 1, this is going to give you a very large value for y cap. And now y cap is, or y cap will explode. On the other hand, if you're going to have a smaller value, less than 1 in this weight, now 0.9, so, or maybe 0.7 or whatever, so 0.700, here also you're going to have a minus 1 into x, and here you're going to have a bigger small value you are going to have. So it means that the weights, by virtue of what values that they are going to have, their composition, it may lead to a kind of a exploding gradient or a vanishing gradient. So now this is also another issue. Now, so it means that if W is greater than I, the activation and the gradients is explode, and if W less than I, the activation and the gradients will. So activation meaning the y cap is going to explode, and then the derivatives are also going to explode. Similarly, if W is less than I, then activation of the gradients will vanish. So, there are ways like where researchers have overcome these by using something called as ResNet and so on. So, now what it does is that it makes the training very difficult. Then and also the gradient descent will also take tiny steps, and it will take a long time for gradient descent to learn anything, right? So these are the problems with respect to vanishing and exploding. Now somebody was asking about weight realization. So now one of the ways in which, because we saw that like this vanishing and exploding gradient is mainly due to the weights, right? So it means there has to be a proper way of initializing the weights, right? So now Now, how is this to be initialized? So now, if we initialize the weights um, uh, with the variance which equals 1 divided by nx, right? So we need to initialize with a variance that equals 1 divided by nx to be the range of w's. So say for instance, like it's initialized in this fashion. So um, so in this fashion, like when, so you have nl minus 1. So nl minus 1 is the number of nodes in this particular layer. So using this, like you try to find out a random element using this as the variance. You try to find out some random values and then initialize these weights, right? So this is one way, like they try to initialize weights and they try to there are other ways that are told, like say for instance, um, if it is initialized with 2 divided by nl minus 1 plus nl. So you look at the number of nodes in the previous layer, the next layer, and use both of them to arrive at variance, and then you initialize the weights with that as the variance. So that is one another way to do. And some researchers have told that using this as the variance to initialize the weights for ReLU, when you use the ReLU activation function, that is better is what some people. So different kind of themes. So say for instance, here you have random shape and np dot square root of 1 divided by n minus 1. So this is one thing. Then you have np square root of 2 divided by n l minus 1 plus. So this is another way, right? So then you, for ReLU you have 2 divided by n l minus 1. So you have 1 divided by n l minus 1. So you have 2 divided by n l minus 1 for ReLU. So so um, so this can also be a hyperparameter, 1 or 2. Which one to use? That itself can be a choice that is to be made. So there are various ways, like here you can also see this initialization. You can also, in libraries that you use, you can choose what kind of initialization that needs to be done, whether Xavier initialization has to be done or he initialization has to be done. This you can choose from the libraries. Right? So basically, how do they work? They work by choosing these one or two, or by varying these NL minus 1 and NL as the variance to choose the weights, and that's how they basically initialize. Now we come to the next thing, which is the numerical approximation of the. So now I think we will skip this particular portion. So gradient checking I'm skipping. Um, so now we will look at the optimization algorithms. Right? So now in optimization algorithms, like we look at mini-batch gradient design. Right? So now training using training a neural network with large data. Say for instance, you have a batch gradient descent. There are various types of gradient descent algorithms that are available. If you have M training examples, now what you can do is you can go from 1 up till m, then you update the weights. So after going from 1 to m, then you update the weights by finding dw db, right? So this is one way, right? So this you call as the batch gradient descent, right? So on the other hand, if you can also do, instead of going throughout the entire data set, you can choose example, one of the examples. Then using these examples, you calculate the loss, right? Then you use this loss to backpropagate, and then try to find out dB, dW, and update weights. So it means for every instance or example, for every instance, what you do is you perform this and you randomly choose the instance. We call this as a stochastic gradient descent. Right? So the weight update is going to happen for every so these are two schemes. So here you have one scheme called as a mini batch gradient. So now if the training examples are very large, very large, then what happens is that the uh, the uh, the optimization or training becomes very slow. It implies that training is going to be very slow. So what you do is, because like you need to compute for, say, using a batch gradient, you need to compute the entire values for all the examples and then perform and weight update, right? So you need to compute dwdb for all the training examples and then divide it by m to compute the values and then perform a update of the weights, right? So it means that the training is going to be very slow, right? So in order to improve it further, like another problem is entire data set may not fit into the memory. So the solution for this is that you split these m into mini batches, and the size of each of the mini batch is 1000, right? So you split the entire input, that is both x and y, into these mini batches, and then you run the batch gradient descent. Sorry, then you run the gradient descent on each of these mini batches, and for every mini batch you do an update. Okay? So update the W and P for every mini batch. So this is what is done with respect to the mini batch gradient descent. So now what you do is you have this number of mini batches, then you do a forward, then you compute the cost, you do the backward, and then you update parameters. So what you can do is now we see that mini batch gradient descent is faster than large data sets. So now when you compute the cost, right? So when J of W P is computed with respect to the mini batch, it will not be a monotonically decreasing as in the batch gradient descent. So in batch gradient descent, monotonically decreasing cost. Now, with respect to a mini batch, you're going to have ups and downs. You're going to have these kind of things. So with every batch, like it may go up, with another batch, it may come down, and so on. So it means that for every iteration, like you're going to have some up downs, even though the trend is going to be decreasing. So the trend in mini batch is going to be decreasing, but not smooth. So the cost function is not going to be a smooth variation. So with this mini batch, you're going to have this kind of. So now so the advantage is that with respect to Minibatch, you have fast learning, and vectorization is basically like you need not compute example by example. You can compute one mini batch as a vector. Right? In one go, you will be able to find out the outputs for all the examples. Right. So that is going to be advantageous. So now. And also, Minibatch can have a problem that it does not always exactly converge. So after reaching the minima, so near to the minima, there it may oscillate. So it may not always converge with respect to Minibatch. It may not easily converge as it reaches the so now, in order to choose a batch, like maybe you can have a small, if you have a small data set, don't go for a mini batch, and use batch gradient. The data set is of less than 2000 examples. Otherwise, you choose a mini batch such that it's powerful. And like so, mini batch size is once more going to be another slide. So now the next idea is called as the exponentially weighted averages. Right? So these are basically optimization algorithms that are better than the gradient descent. So far, like we've looked at the gradient descent optimization. So basically, like we find out that W is equal to W minus alpha into BW. So that's how we compute the gradient descent. So as for V, right? So now we have a few other optimization algorithms which are better than the gradient descent optimization. So here, like let's assume that you have some temperatures, right? So maybe like for every day, so first day 40, and so on. Like you have a set of temperatures, right? So now we can plot these temperatures, and you can find out these outputs can be, right? So say when you plot these temperatures, then you're going to have some values. So values so like this. So now you're going to have these temperatures. Now, now, if you compute something called as an exponentially weighted average, so how do you compute the exponentially weighted average? It's computed by, say, V naught, by assuming first of all V naught is, and now V1 is equal to 0.9 into V naught plus 0.1 into P of 1. Right? So what are you given? You are given T of 1 is equal to 40, T of 2 is equal to something, and so on. This is what you are given, and T of 180 is equal to 60. So in order to you use this, right, and you compute V1, right? So V1 is going to be 0.9 into V0 plus 0.1 into T1. So it means it's going to be 0.9 into V0 plus V0 is 0, so this entire thing is going to be 0. and here you have 4. So now V2 is going to 0.9 into V1 plus 0.1 into 9. So into 49. So we have V1 is 4. 4 into zero point 0.9 is 3.6 plus 0.1 into 49 is going to be 4.9. So this is going to be equal to 5 and so on. So this way, like you keep calculating the exponentially weighted averages. These you call as the exponentially weighted averages. So now in general, we can write this equation. So in general, we write this as V of t is equal to beta into V of t minus 1 plus 1 minus beta of so for t of t or t of 1. So you have this function. So it means you have two more hyperparameters, beta or one hyperparameter beta, or one more hyperparameter which is beta. So now using this, like having calculated for all say 180 days, you can once more plot the so you can plot it maybe like this. So a little bit of wiggles is there. So you are able to plot it and so basically this V and T also both of them correspond to each other, and we are able to plot it in this. So now if we vary beta, so if beta is equal to beta is equal to 0.9, what it means, what it implies is that it represents so or like the value if beta is equal to 0.9 and the values that you compute, that is V of t, it represents the average over last 10 entries. So for P of t, it represents the average over last 10 entries. So how do you know it is equal to 10? It is computed by using 1 divided by 1 minus beta. So for whatever the beta is, if beta is equal to 0.9, how many days average does it conform to? It can be found out by 1 divided by 1 minus 0.9, which is equal to 1 divided by 0.1, which is equal to now 10 represent 10 as the number of entries whose average is going to be denoted by V of t. So similarly, if you compute V of t by taking beta is equal to 0.98, then you can say how many days average it may represent. So in that case, you can find out 1 divided beta, which is equal to 1 divided by 1 minus 0.98, which is 50 days, right? So this represents the average across 50 entries, right? So the entire plot, if it is done, right? So the entire plot, if it is done, it's going to be more smoother than this plot. So it's going to be further smoother than the previous plot. On the other hand, if you had taken beta equal to say 0.5, then it's going to denote the average across 2 days. And in that case, like you're going to have a plot which is going to be like this. So this is going to more overfit the given data. So it just represents a moving average over only 2 days. So now we can say that like the best beta which we can have is 0.9 and 0.98. So now the reason why they are useful is that uh, they can give different weights to recent data points based on the value of beta. So I can choose beta, and I can determine like what should be the uh, uh, weightage that's to be given to the recent data points, right? So if beta is very high, so it smoothens out and it averages the skewed data points, right? So it does away with the oscillations. It reduces the oscillations, right? And it means that, say, basically, like as you have this contour, if you choose the W and B, and as you move towards this global minima, you basically the gradient descent basically oscillates. So now you don't want this kind of oscillation. Rather, you want a smooth passage from this point to this point. So with minimal oscillations, if there can be a passage, is the idea. So now one way to do this is to only oscillate as much as based on the weighted average, right? So if you use this weighted average concept within um, this within this gradient descent, or in addition to the gradient descent, then it makes the path towards the minima. So now here like we can further see this way. This is the way it is computed. So into t minus 1 plus 1 plus beta into t to t. Right. So we have V100 that is computed in this fashion, V99, V98. So now you can, I mean, statistically, like you will be able to arrive at if you expand these expressions, like you'll be able to arrive at these equations. So I'm just algorithm is quite straightforward. So we can compute this. Now there could be some biases. Right? So now, say for instance, like if this graph, if the average becomes very close, then it may introduce some biases. So we want to do away with this bias. Say for instance here. So what is the average? It is going to be 40, 49, 45, 60. But then we are starting with basically on this 4 and 4.9 and so on. Right? So it means that there is some bias in these values that are computed. So they should be more closer to these ranges rather than far away from these ranges. So this you can call as the bias, right? So what we do is like we try to do this kind of bias correction. So in order to do this bias correction, what we do is we use this equation. So it means that we divide these terms by 1 minus beta power. So now as t becomes, so it means that initially your t is going to be smaller, right? So that much you will be able to remove from 1, right? So and this will cause the value to grow more. The numerator will be larger than the denominator, right? And as the iterations, as you keep finding out the values for more t's, what will happen is the effect of the denominator starts going out. So initially the effect of the denominator will be high, so which will make the expression become larger, and as the effect of the denominator becomes low, the numerator no more tries to become larger. So you have this kind of a thing at the bottom. This you call as the bias correction. So we come to this idea called as the momentum. So momentum is another algorithm which works faster than the standard gradient. In with respect to momentum, you calculate the exponentially weighted average for the gradients and update the weights with the values. So basically, like what you do is you calculate this VDW. So you initialize this VDW and VDV with 0, and then in the subsequent steps, you calculate this new VDWs. So from the VDWs and DW. It means you already have DW, and from these DWs and the previous VDW, you calculate the new VDW. Similarly, you calculate VDB from the previous VDB and the currently computed. So after computing this VDW and VDB, what you do is you update W equal to W minus alpha into VDW. So earlier the equation was W equal to W equal to W minus alpha into dW. So now we are doing away with dW. We are substituting this dW with the VDW, and this is said to be more representative of the weighted average rather than the current differentiated. So it means that this sort of creates a momentum, right? So it helps the cost function to go to the minimum point in a more fast and consistent way. So now, because like it helps, what happens is beta becomes another hyperparameter, and beta equal to 0.9, and it works very well in most cases. So now another optimizer people use is called as the RMS prop. So here with respect to RMS prop, you calculate two more variables which are SDW and SDP. SDW and SDB. So using these, what you basically do is you compute dW square, right? So in the earlier case, when it was VDW, it was dW. So basically, we had rest of the equation, rest of the variables is the same as VDW, VDW plus 1 minus beta into dW. Now you have dW square, right? So this is the way like you compute the SD, and then you perform a weight updation. So how do you perform? Earlier learning rate into VDW. Now what we have is dW divided by square root of SD. So we have the weight update that is based on this um, this kind of change, right? So this you call as root mean square prop. So you have another thing which you call as the root mean square prop. So I'm just skipping. This also has a similar kind of a behavior that it enables faster movement towards the minima instead of lots of oscillations along this. Now, the next thing is called as the Adam optimizer. So Adam optimizer is another optimization algorithm. So now, this also works well with the networks. So this is an amalgamation of both RMS prop and the so so it both puts the RMS prop and momentum. So we see here that we compute both these variables. V was earlier computed with respect to momentum, and SDW, SDB were computed with respect to RMS prop. So in this particular case, we compute both these, and what we do is like we compute these both things. So just as we computed earlier, so it's the same format, like we compute this, and then over here, like we also fix the bias. So there is a bias correction that happens using the same function that we studied earlier. So the bias is corrected with respect to the momentum, and also with respect to RMS prop. And finally, like you have a weight update, which is W equal to W minus alpha into PDW divided by square root of SDW plus epsilon. So you have uh, this kind of function. So now it means that there are two betas here. So one is beta 1 with respect to momentum, and beta 2 with respect to the RMS prop. And you have some values like these which are recommended by default, and you also have a epsilon value that is also recommended by. So now all these different optimizers are set to work faster than standard gradient. Now you know like why, which one, or why you should not use the standard gradient, because you have better optimizers like which one better than the standard gradient design. Now, the next thing is the rate decay, right? So now we need to, we may have the learning rate. So learning rate, say for instance, when the learning rate is in the initial times, you should be able to move faster, and as you come near to the solution, you should be uh, moving slower, right? So otherwise, if the learning rate is the same everywhere, if the solution is here, you will overshoot the solution, right? So now once more you'll have to go back, and once more you may overshoot, and once more you may go back. So this way you may never arrive at the minimum, right? So now you have different ways in which like can reduce the decay rate, right? So you have the learning rate, instead of being a constant. So far, like in all the neural networks that we've studied, you keep the alpha as a constant, right? So now what you do is like you can have different learning rates with respect to the epochs, right? So in one epoch, you have a higher learning rate, and as you go further, like the learning rate may come down. So you can have these kind of learning rates. So 1 divided by 1 plus decay rate in epoch number. So 1 divided by this into learning rate, right? So this way, like you have a function which sort of reduces the learning rate. You may have different types of these functions. So you may have a learning rate which is given by any of these functions. Right? So I think like with this I'll close. So batch normalization is another kind of scheme wherein you see in the earlier case we studied normalization. So we normalized the inputs. Right? So why only inputs? Cannot we normalize the activations? Right? So cannot we normalize the z values? Right? So these are the questions that are asked, and we try to perform something called as a batch normalization with respect to normalizing the z values, right? So now you look at the hyperparameters. We have learning rate, momentum, mini batch, number of hidden units, number of layers, and so on. Learning rate decay, regularization lambda, activation functions, ADAM, beta 1. So we earlier we started with something very small, right? We just knew the number of layers, right? So we knew the number of layers, we knew number of hidden or number of hidden layers, number of hidden neurons, right? We knew maybe the learning rate, right? So, but as you see here, like there are several types of hyperparameters that are possible with neural network, right? So it's very difficult to decide which hyperparameter is to be optimized and how to optimize. So now one way is to do you use this some of the hyperparameters, then you select one of the hyperparameters, you check like for various values which one is working better, then you choose that one and you continually move on, right? So this is one way in which like you can tune with respect to the hyperparameters, right? So with that, like I'll close for this session. So I will meanwhile like I'll share with you a PDF. So you can kindly go through that PDF. So, so this particular PDF, like I'll be sharing with you. So you can go through this PDF. So at the end of this PDF, there are few tasks that are given, right? So now I would request all of you to go through these tasks and perform the um, operations. So I mean, perform or like do whatever that has been mentioned in those tasks. Right? So basically, like here you have a neural network that has been created from Keras, right? Using Keras libraries, they have created the neural network, right? And they have normalized the values. That is something that we studied, right? Then they used a linear regression model, and they tried to fit the examples onto the linear regression model, and also they also created one deep neural net model, and then they tried to fit the inputs. So meanwhile, like how are we going to do this lab? So um, you all may have Google accounts, right? So are you all familiar with Google Colab? So yes. So then like so basically like the steps are quite simple, right? So I don't know like if how many of you will be familiar. So just go to Google. Uh, um, and so after doing this, connect, then click connected to a host runtime, hosted runtime. So if you want to command, then you can see what all have been installed already over here. So here you can find out that um, you already have TensorFlow, TensorBoard has already been installed. So it means that you don't have to install anything new. So you can start with using TensorFlow. Then you also have sklearn, pandas, then scikit-learn. All of these libraries have already been installed here. So since they've been already installed, so what you can do is you can you can take up this code. I'll be sending you the library. I'll not be sending you the PONB. So you will have to go through this thing, and you will have to install. I mean, you'll have to run the code and perform the tasks that have been mentioned over there. And you, all of you, like you should submit me a report, right? So this is your this is part of your assessment, right? So based on the tasks that you have performed, like you send report. So today, like I'm just sending you a Keras code. Maybe in the coming days, like other people may work on PyTorch also. So if you can, if you want, like I can send you a basic tutorial on PyTorch, like that also you can kindly go through. Is that okay? Will you be able to do it? Hello? share the code for our references. I'll do that. So with that, like I think I'll close for today. I think I'll be right away. I'll be sending you the code. So if you have any questions, you can just ask me. Yeah, just stopping my sharing because we've learned so many things today. So we can. No, please don't run the notebook and send it to my email ID. So I'll be sharing. You create a report in the sense that whatever tasks that have been told, you write it as a question and you write what are your inferences, because basically whatever that has been asked is some kind of an inferential thing only. So no, I'll not be sharing the Jupyter notebook. So I'll be sharing you the PDF, which I've created from a Jupyter notebook only. Yeah, any other queries like regarding whatever that we learned? I think one thing which we have left out is something called as loss function. So loss function is not touched much today. So uh, so so loss functions like for loss functions also, like I'll just or like we have some time, then we can just go through the loss functions. So I have already sent you the assignment. So on your email ID is like I have sent you the assignment. So just go through it, and I will be sharing with you a link, maybe a Google Form link, and all of you shall upload your reports or a document that you create on that page, right? So don't send it to any of my email IDs. So kindly upload it on that link. So I'll just take a few more minutes to just appraise you about the loss function. So I hope like you'll be able to spare some time. Because that is also an important. So or I think my screen is not working. So just discuss these loss functions. So there are loss functions like that are used for say regression, and maybe you can say classification, and maybe multi-class classification and binary classification also. So if you look at regression, then you have loss functions like mean square error. So then you also have mean square logarithmic error and mean absolute error loss, right? So there are these three widely used loss functions. So now mean square error, we know that like it's going to if there is a loss, then it's going to uh, say it's going to say if there is a difference, because we already saw today in the morning that a loss function is going to say what is the deviation with respect to the expected output. So if you take the mean square error, then we see that it's going to penalize a lot, right? So it's going to, because it's going to square the difference. So it's going to penalize in terms of the backward propagation, right? So mean square error is one such loss which will have a large penalty because of its square difference. Now, the other kind of loss is the mean squared logarithmic error. So what you do here is whatever output that you have, you take the logarithmic of the predicted variable, and then you compare it with the other one to find out the error. So because you take the logarithm, so what happens is because you take the log, the difference becomes lesser. So that way the penalty also becomes less in comparison to the mean square error. Then another kind of error that you calculate is called as the mean absolute error loss. So say for instance, like if there is an outlier prediction or whatever, then it tries to calculate the average of the absolute difference between the actual and the predicted value to find out to give us the error. So similarly, like you also have with respect to binary classification, you have a binary cross entropy loss, right? So the kind of loss that we saw in the morning, that is basically a cross entropy loss. So the loss which we derived in the morning. So that is a cross entropy loss. So with respect to a binary classification loss function, you may use that loss. Or if you have the output variable in the type of 1 or -1, right? So instead of 0, 1, if you have 1, -1, then use for SVM, they used to use a loss function which is called as a hinge loss. So that loss can be used for those kind of values. Similarly, like if you have a multi-class classification, then there are few types of loss functions that are possible. One is similar to cross entropy loss. Similarly, for multi-class classification, you have a categorical cross entropy loss. So basically, if you have more classes, then you have the same formula. Similar to the cross entropy loss, you have a categorical cross entropy loss. One widely used multi-class classification loss is the Kullback-Leibler divergence loss. So this is one another type of loss that is being widely used for multi-class classification. Right? So, and these are some of the loss functions that that are used in various applications. Yeah. So basically, like we saw three types of loss functions. One is the regression loss function, then binary loss function, then multi-class loss function. So with respect to regression loss function, we looked at mean square error, then mean square logarithmic error, then mean absolute error. Then with respect to binary classification loss, we have binary cross entropy loss. Then you have the hinge loss. Similarly, like with respect to multi-class classification, you have a categorical cross entropy loss and Kullback-Leibler divergence loss. These are most commonly used loss functions. So if there are any queries, like then just ask. Yeah. Now, with respect to assignment also, and with respect to whatever that was taught. Yes, all the three tasks you should be doing. Yeah, that's right. Yes, I think like the data is sufficient because like the dataset link is already there. So just let me go through the code for the run the no run the Jupyter. Please share the document. You do the test and document. Feedback, like feedback on the last day, you will get a feedback, I think. So feedback on the portal itself, you will do a feedback. Recordings I will share you. So attendance, like attendance, as I told you, automatically it will be done. So please send through the following mail IDs. So I think I will be sending to all the registered email IDs. So please use your registered email IDs. That will be convenient for me. So there are three tasks. Okay, is the data given in the PDF sufficient? Yes, data is sufficient. Unable to copy it. I didn't get that. Unable to copy the link. Yeah, PDF, like you may not be able to copy the link. Yeah, that may be the problem. That may be a problem. So on 9th, like the assessment will be, it will be a, you will be given probably 1 hour time and you will be asked some questions. It will be an objective type assessment. So do you want me to send the links separately? Links for the data set?
Sir, you can if you can send, kindly send.
Yeah, I'll do that. Yeah, I'll.
Send the submission link as well, where we suppose
Send submission date I've already mentioned, tomorrow evening 5 o'clock. So I'll be sending yeah, I'll be sharing you a link on which like you should submit. Right, that maybe little later I'll do that. So meanwhile I'll share with you the things. Don't have any respect to us what I'm supposed to do. Okay. So see Basically, like as I told you, did you observe that what I told with respect to the Google Colab? Uh, I think there was an email from Mrs. Praveena. So she was saying that she was asking for instructions on what and how to do. So first thing is like you should be able to use your Google account to go to Google Colab. Yeah, just I'm sending the link, the submission. Yeah. So in the same, okay. Submit, so can we submit the email? Okay, I'll just try to go through the assignments. Okay. So so there are you able to hear me? Hello.
Yes,
Yes,
sir.
yes,
The
sir.
sound is not
Yeah,
clear.
yeah. So there are two models that are specified in the PDF, right? So one is a linear regression model, and another is a linear regression that is done by a neural network. Is that right?
Yes, sir.
Yeah. So you can just compare the performance of both these, and then say like which one is doing better or whatever. I mean, so that is the first thing. So now the second task is basically to change the number of layers in the deep neural network and the number of nodes in each of the layers. So now there are two goals that are specified. One is to lower the loss against the test set, right? The second thing is minimize the overall number of nodes in the deep neural net. So basically, like it is similar to our dropping, right? So you try to see like with what number of total number of nodes, like it is able to. You just try saying that, okay, I reduced in this layer this many nodes, and this was the result. I increased it to this many nodes, and this was the result. I mean, so you don't need to optimize the number of nodes. So basically, like with various layers, you try to vary the number of nodes and say like what the results are. Is that okay?
The question is clear. When we'll do, then we'll see how much we will be able to do.
Yeah. So I think like you should try it. That is the ultimate goal. So you please try. The third thing is the regularization. So today we looked at various regularizations. So basically, like you already have some regularization libraries. So you just import those libraries and use those libraries in the model. So then you may be able to say like and say like what the results are. Is that okay? I mean, so the three tasks.
Yes, sir. Yes, sir. You have to submit by tomorrow evening, I think.
Yeah, by tomorrow evening, 5 o'clock.
Yeah. So I think we may leave meeting now, and we should work like.
Yeah,
Then we have to submit this.
yeah, yes,
Okay.
yes. Yeah.
Okay. Thank you, sir. Thank you.
Thank you. If you have any queries, like you can just ask. Otherwise, you can.
If we'll face any problem, we'll ask you in the morning, the session.
We will try
Session
and
though tomorrow you will have new speakers. Yeah, you can
Okay.
put it
Okay.
in the WhatsApp group. I mean that will also be okay.
Yeah, perfect, sir. Thank you. Thank you, sir.
Sir, we got a
I'll,
mail which saying that assignment you have to submit tomorrow. Something
yes.
saying. Is there
Can
any
you?
assignment?
Yeah, this is the assignment. The lab one which I have shared you. That is the
Hmm.
assignment. At the end of the PDF, you can find few tasks to be done. Those are the tasks you have to do.
1 minute, sir. I am going to that PDF.
Yeah.
PDFs are containing only the programs only, I think. Task is there.
हाँ वो टास्क को खत्म करना है.
Okay, sir.
Creating tensors in
Okay, sir.
Creating tensor in PyTorch.
Thank you, sir.
That means calculating
Yeah,
size
thank
and
you.
variable. That is the task, sir.
Yeah, I could not hear you clearly. Can you please repeat?
Sir, I am telling that creating the tensors in the PyTorch. That is the calculate
No,
the
no,
size.
no. PyTorch is, I mean, that is a complementary kind of a thing. You can just go through that document because tomorrow, day after tomorrow, we do not know whether those speakers and those assignments will be on PyTorch. So if at all they are on PyTorch, you should have some idea of PyTorch. That is why I had sent the PyTorch document. So before the PyTorch document, I had sent you lab one. That was the assignment. There was another lab.pdf. Yeah, LABB, lab.pdf. So that was the assignment.
Sir, please can you tell me the
Can you tell me?
what is the assignment?
Yeah, the assignment is if you go at the end of that lab, there are 3 tasks that are mentioned. In page number 9, I think. 9 or 8 in your document.
Number 9, sir. Yes, sir.
Yeah. So there, like you have first you're asked to compare the two models. So in the above program, there are 2 models. One is a linear regression model. Then you also have a neural network model. So you just run the programs and compare like which one is doing better. Whatever your inferences are, you please write down. If you can have some comparison graph or something, you can put. Otherwise, however you can compare and write the results. Then the second task is to optimize the neural network topography. Actually, you are expected to reduce the number of layers and optimize the thing. What you can do is you vary the number of layers, vary the number of nodes in each of those layers, and see like how the neural network performs and write your inference. Then the third thing is to use the regularization. So there are 3 types of regularizations that are mentioned. So now you implement the L1 or L2 regularization by importing those libraries and then using them in that code as it is specified, and then say what the results are. Is that okay? Could you hear me?
Okay, sir. Yes, sir.
Yeah.
Are you going to share the
Are you going to share the?
today's session contains PDF file which you shared on
Yeah,
yesterday?
PDF I can share. That is not an issue. I will share with you the PDF.
Thank you.
Yeah. So I've already shared the PDF.
Sir, received. Shall we leave now?
Yeah, you can leave. Yeah, if you don't have any queries, you can leave. Yes, Mr. Ramesh, I have shared it in the mail. So I have sent you the IPynb files. So you can take it. I mean, so you can directly copy from the IPynb files. Hello, am I audible?
Yes, sir, you are audible.
Thank you. So with that, like, shall I close this session? Any more queries are there?
Any more queries are there?
Sure, sir.
Thank you.